Hello everyone. In the last lecture, we had seen what is resistivity methods, how resistivity of the subsurface of the earth is controlled by various factors. Right? That is what we had seen in the last lecture toward the end. And apart from the factors which we have considered, right, the flow of current beneath the subsurface is somewhat similar to flow of water. That is why there is a kind of good comparison between the electrical properties and the hydraulic properties, or in other words aquifer properties. Aquifer properties is the most apt word, right? So here are the electrical properties, here are the aquifer properties, right? So what are the important aquifer properties? Aquifer properties are transmissivity and hydraulic conductivity. So what is hydraulic conductivity? Hydraulic conductivity is the ability of the formation to transmit water. What is transmissivity? Transmissivity is the ability of the formation to transmit water along unit width of the formation. Whether it is hydraulic conductivity or transmissivity, we are referring to how in the subsurface groundwater is flowing in the formation. This is related to the way in which current is going to be transmitted by the formation. So, transmissivity of the formation is related to transverse resistance. Transverse resistance. Similarly, the leakance, that means the leakage of water in the vertical direction below the surface, is related to longitudinal conductance of current. Right? Very interesting, isn't it? So, there is an analogy between the way in which current flows beneath the subsurface is related to the flow of groundwater. So, what is equivalent to hydraulic conductivity? Here we have aquifer resistivity. Resistivity of the aquifer, which we measure by electrical resistivity method, is related to hydraulic conductivity. Okay, so it throws the greater potential for the application of resistivity method to understand about the groundwater occurrence below the surface of the earth. And here is a diagram brought out by these people, right? It gives us the approximate ranges of resistivity of different geological material, right? In the x-axis, we have resistivity given in ohm meter, starting from 0.01 ohm meter up to 100,000 ohm meter. As we were discussing previously, what are all the factors that control the resistivity? We had seen the role of force as well as intrinsic resistivity of the material, right? As you seen here, the metals of sulfates have lowest resistivity. Then we had also seen the quality of water, quality of groundwater also is one of the important factor that control the resistivity which we measure. So here you can see salt water is having very low resistivity. So if salt water is present below the surface of the earth, resistivity which we measure will be very less, isn't it? It will be very less. Then clays. Why clays are having low resistivity? Because we had seen already the porosity of clays are much higher. Porosity is much higher, nearly 50%, since the volume of the pores is so small. Individual pore, I mean the individual pores volume is so small. Water which, or the moisture which got entrapped in that, is unable to escape easily. Until otherwise, you have some heat energy, right? At the surface, the clay may appear dry. You may have some you can see some cracks in agricultural fields during dry period, right? But beneath, still moisture will be retained, due to which resistivity is less for the clays. How about for rocks? The common rocks which we see in our mountains, or the rocks which we use as a building material, the resistivity is very high. Resistivity is very high. Similarly, when the same water freezes and it becomes ice, resistivity is very high. So, in fact, resistivity method can be understood to see whether beneath the surface groundwater is in liquid form or in frozen form. The word permafrost refers to permanently frozen groundwater below the surface of the earth. So, this is the surface of the earth, this is the water table, right? This is the water table, but the water here, which is groundwater, when it is in liquid form, the resistivity will be somewhere here. When it becomes frozen, resistivity gets increased. Okay, so this figure gives us approximate ranges of true resistivities. Please remember, we are discussing about true resistivity, but can we measure true resistivity of the subsurface? No, we cannot measure the true resistivity. We can indirectly arrive at true resistivity. How, we are going to see little later. So here is approximate ranges of true resistivities of different formations, which are shown in this diagram. Right? Now, after having looked into some fundamental aspects of electrical resistivity method, let us actually deep dive into how the survey is carried out on land to understand about the subsurface. What we are going to do is, as you can see in this picture, the green line shows the surface of the earth, right? This is the ground surface. We are going to choose 2 points, right? Let us assume this is point A and this is point B. We are going to apply current between these 2 points, chosen points, which are A and B. Right? Current is going to be applied. How are we going to apply current? We are going to connect a battery to this circuit, and we also measure the applied current here. Right? Now, as we have started applying current, current goes into the earth, as you see here in this diagram. The flow of current generates some potential, right? Some potential is developed due to the applied current. The developed potential is measured between these 2 points M and N, right? Using a voltmeter. Here we had a current meter to measure the current that we apply into the earth. Here we have a voltmeter to measure the potential. Right. Now we have both V and I. We can determine what is the resistance using a meter known as resistivity meter. Very simply, I am explaining now here about the method, right? Then we have to calculate apparent resistivity. How can we calculate apparent resistivity? Using this circuit, we have measured R, which is the resistance. Resistance is going to be related to apparent resistivity. How is it going to be related to apparent resistivity? With one constant known as K. If you multiply the resistance which we measured for this circuit with a letter K, then we can determine apparent resistivity. What exactly is K? K is dependent on how we are going to arrange the electrode. So I didn't introduce what is electrode. I was telling you we are applying current through point A through point B. How can you apply current into the earth? We need a small arrangement which is nothing but electrode. So electrodes are nothing but a rod, a conductive rod, maybe like a miniature version of the cricket stump, right, which all of you are aware of. So it is a rod, a conducting rod of length of about 40 centimeter, a diameter of 1 or 1.5 centimeter with a spike at the bottom so that it can be easily hammered into the earth. It is something like this, right? So this is an electrode. So this electrode will be hammered into the. Now where are we going to place them? In this picture, this is A and this is B, right? Each one of us can use different distances between them, isn't it? Right? So the value of resistance which we are going to measure will vary. For example, now I have placed A and B. Let us assume they are at a distance of 10 meters. You may keep them at 8 meters, or another person may keep the electrodes at 20 meters away, right? So all of us are going to get different values of resistance for the same earth. We are doing the survey at the same location, but we are going to have different resistance, which means the resistance which we are obtaining is controlled by the distance between the electrodes, isn't it? So the constant K depend on the way in which we are going to arrange our electrodes. That means, in other words, to put it straightforward, the electrode arrangement refers to the distance between A and B and the distance between M and N electrodes. Right. Many researchers have suggested different methods of arranging the electrodes. Some of them are, one is called as Venner method of arrangement, Schlumberger method of arrangement, dipole method of arrangement. These are some of the popular methods of electrode arrangement. Now let us see what are the instruments that are necessary for carrying out the electrical resistivity method. I have been repeatedly telling it's a active method. What is active method? We are going to send some signals. Here what signal we are going to send? We are going to apply current into the earth. Obviously, so we need a power source. Right? We need a power source. We may use a generator, right? Or we can use a battery, right? A 12-volt battery which we often use in our automobiles. Maybe a car battery itself will be sufficient as a source. So first and foremost is we need a source, as we had seen previously, right? This is B, this is point A, wherein we are going to apply current. So we need a battery to apply a current. So first and foremost is a battery source, that is a direct current, or we can also use a generator to apply alternate current, but very commonly we use a battery. So it is so portable, very easy to carry, isn't it? So in most of the surveys, more than 99% of us, we use only battery as a source. Then what else is necessary? We need to measure the current applied, for which we need a ammeter. Then what else we need? We need to measure the developed potential, that is done by, so we are measuring the current applied using an ammeter, and the current flows from the battery into the earth. That creates some potential These are the equipotential lines. This potential have to be measured. That we are measuring between these 2 points using a. So we need an ammeter and voltmeter. Are we really using them today? That was the case nearly 30 years ago, but today both of them are interrogated, and today we have modern resistivity meters. Right? So this, you can see a picture of a very popular resistivity meter. In resistivity meter, we literally don't know where is ammeter and where is voltmeter. Both of them are combined, and the meter directly gives us the resistance or apparent resistivity. Okay. Then the next is electrodes. I had already told you electrodes are nothing but conductive bars, may be made of stainless steel or aluminum or brass. They are of about 30 to 40 centimeter length with a sharp edge at the on one side. Okay, so that this can be easily hammered into the earth. We can just use a hammer to drive it into the earth. Okay, so this is how we make a good connectivity between the battery and the earth. So you cannot go and leave the wire on the surface of the earth, isn't it? So instead we hammer a conductive rod into the earth up to maybe about 10-15 centimeters below, right? We hammer so that the connection is intact. Then we need some cables. What cable? Because we have now inserted the electrode, this has to be, there should be a clamp and a cable. The cable should be connected to the resistivity meter. Okay, so resistivity meter has got 4 knobs as you see here, right? 2 for connecting current electrodes, 2 for potential electrodes. Okay, that means I will connect them to this, right? These are the current electrode. So I connect one here, another one to this current electrode. This is the potential electrode is connected, right? So this is how we connect all the 4 electrodes to the resistivity meter, for which we need sets of cables. We may keep the electrodes at different distances. Okay, so we need cables in the form of a spools for easily managing the wires in the field during the field work, right? So the wires are wound on these spools. The spools are used to connect the electrode with the resistivity meter. Okay, so here also you see pictures of electrodes. So here it is a very thin electrode, maybe 0.75 centimeter to 1 centimeter in diameter, length may be about 40 centimeters. So here also you see pictures of electrodes. Is it clear? So these are the instruments that are necessary to carry out the resistivity survey. Most important one is the source battery. Then we need a resistivity meter. Then the third is we need some electrodes. How many of them? At least 4 electrodes are necessary. As you see in this picture, 2 to apply current, 2 to measure the potential, right? Then we need some sets of cables. Of course, we need also a measuring tape, because we need to measure the distances between the electrodes. So these are the equipment that are necessary to carry out the resistivity method in the field. How we are going to arrange the electrodes? We have already seen what we measure is only the resistance, but we are able to determine the apparent resistivity using the measured resistance. How? we have seen apparent resistivity rho or rho A. Normally it is referred as rho A is R multiplied by K. We said this K is dependent on how we are going to arrange the electrodes. So let us see about arrangement of electrodes, right? Here in this picture, you can see electrodes are arranged in such a way, right? The outermost ones are current electrodes, which are usually referred by letter A and B. Inner electrodes are known as potential electrodes, which are referred as M and N. Right? This is how we make the measurement. So here is an example of carrying out a laboratory measurement. But how are we going to do in the field? In the field, we had already seen the three popular methods of electrode arrangement. First is the Venner arrangement. So according to this person who suggested this method, Venner, according to this method, all the four electrodes are kept at equal distance, isn't it? So you can look at the picture here. This is A, right? A electrode, B electrode, and in between we have M and N electrode. What is the distance between all of them? The distance between all the electrodes are the same, A. If electrodes are arranged in this manner, then this electrode configuration or array is known as Venner configuration or Venner array. Okay. Now let us see the next method of arrangement, which is Schlumberger arrangement. In Schlumberger arrangement, according to his research and suggestion, right, the distance between the electrodes are as you see in this picture. In other words, very simply, we can put it like this. The distance between the electrodes M and N is greater than distance between the electrode M and N is related to the distance between A and B. What is the relation? The distance between A and B is greater than 3 times of Mn. Okay. What do I mean by 3 times of Mn? So here, what is the distance between all of them? The distance between all the electrodes are the same, designated by small letter A. Whereas here, the distance between A and B is greater than 3 times of this distance. If you write the same notation for Venner arrangement, how can we write? So we will write as the distance between A and B is equivalent to 3 times of Mn. Okay, am I right? So for Venner arrangement, which you see here, right, the distance between A and B electrode is equivalent to 3 times of the distance between Mn, because this is A, this is A, this is A. So the distance between A and B is 3 A's. Okay. Whereas in Schlumberger method, the condition only stipulates the distance between A and B electrode has to be greater than 3 times of Mn. As I have written here, the distance between A and B needs to be greater than 3 times of M and N. Okay, M and N electrode. So what is the major difference between these two methods? So in the first method, distance between the electrodes are same, whereas here it is not. Okay. Then the another configuration known as dipole-dipole configuration is a little bit different than the previous methods, because here current electrodes and potential electrodes are kept kept as separate pairs. Okay, whereas in the previous method, potential electrodes were arranged between the current electrodes. Whereas here, current electrodes are a separate pair, potential electrodes are kept as a separate pair. Okay, now we have seen how electrodes are arranged in these three important electrode arrangement method. We have already said resistance which we measured can be converted to rho A only by apparent, that is apparent resistivity, only by multiplying resistance with a K. We said K is dependent on the way in which the electrodes are arranged, isn't it? So here in this arrangement, we can see K is equivalent to 2 pi A. In this method, K is equivalent to this, right? This can also be written in another form. So, as we discussed previously, the electrode arrangement helps us to arrive at the value of K. When you multiply K with the resistance which we measure using the circuit we have formed at the ground, we can arrive at the resistivity of, apparent resistivity of the formation, right? So in this picture, again, I am showing you how some popular ways of electrode arrangement. I am showing one more picture. This is dipole-dipole arrangement, current electrodes, potential electrodes. Then another method known as pole-dipole-dipole method. Here, one of the current electrode is kept at greater distance somewhere. At great distance, one current electrode is kept, whereas all the other three electrodes are moved over the area. Then pole-pole method, similar to previous method, both current as well as one potential electrode is kept at greater distance. Then Venner method. In Venner method, we had seen just now, all the four electrodes are kept at equal distance. In Schlumberger method, potential electrodes are kept closer to each other. Current electrodes are at distances greater than 3 times of Mn. That is Schlumberger method. Okay, it shows one more on this. Researchers are going on inventing newer and newer methods, right? Here is Venner method, and then subsequently they came out with what is known as Venner beta method. It is something like dipole-dipole. Current pairs is taken separately, potential pair is taken separately, but the distance between them is maintained the same. So it is a Venner beta arrangement. Similarly, we have gamma arrangement, Venner gamma arrangement. In Venner gamma arrangement, current potential, right? So like this, you see different arrangements in this slide. So why we are coming out with several methods of electrode arrangement? Each and every researcher try to innovate and coming out with a newer method of arrangement. They claim that they are able to achieve something that was missing in the previously identified electrode arrangement method. Okay. However, though there are many electrode arrangement methods, most popular electrode arrangements which we discussed previously are Venner, Schlumberger, and dipole-dipole. These are the three most popular methods of electrode arrangement. Thus, during this lecture, we had a look into some of the factors that control the electrical resistivity. Especially, we had a look into how electrical resistivity measurements help us to understand about the aquifer parameters. The most important aquifer parameters are hydraulic conductivity and transmissivity. Then we had a look into how resistivity investigation is carried out on the land surface. Then we had also seen what are the different methods of electrode arrangements, how different electrode arrangements are used, and accordingly what are the electrode arrangement values K, which is the constant. Then we had also briefly looked into this particular slide some variants of Venner method as well as pole and dipole method. Thank you so much.